Welcome back, kids. In the previous lecture, we have discussed about the transformation of coordinates of a point from Cartesian to cylindrical and also to spherical systems. And also we have done the vice versa also. We have seen the conversion of coordinates of a particular coordinate system to the other coordinate system. So we have done problems on Cartesian and cylindrical and spherical coordinate system. In today's video lecture, we will solve some more problems so that you will get familiar with these transformation between coordinate systems. We will see how to determine the spherical and cylindrical coordinates when Cartesian coordinates are given for a point in a free space, and also we will try to transform the vectors from one coordinate system to another coordinate system. Now, we will see the first problem here. The first problem states that determine the cylindrical coordinates of the point whose Cartesian coordinates are given by x is equal to 3, y is equal to 4 and z is equal to 5. If you carefully see, the given what they are asking is, they are just asking us to determine the Cartesian, they are asking to determine the coordinates of a point. So, this represents a point. Let us suppose x is equal to 3, y is equal to 4, z is equal to 5. This is a point, or what we can represent as p, x, y, z in terms of 3, 4 and 5. Now what he is asking to convert it into cylindrical coordinate system. So it is only a point coordinate conversion. So we have seen the formula in the last class itself, that when we want to convert it into cylindrical coordinate system, what do we require? We do require r, small r, phi and z. And what is the formula for r? R is equal to square root of x square plus y square plus, x square plus y square. So see, r square is equal to x square plus y square. X is 3, y is equal to 4. So 3 square plus 4 square, it is 5 square, 25. So if I want r, then I will be taking it as phi. Similarly, phi. What is the formula of phi? Phi is equal to tan inverse of y by x. So first of all, I am computing tan phi, which is y by x, which is 4 by 3. Once it is done, phi is equal to tan inverse of 4 by 3, 53.13. Now, z remains the same for both Cartesian and cylindrical coordinate system. So it is already given as phi. So its value is phi. So now r is equal to 5, phi is equal to 53.13 degrees, z is equal to 5. So the coordinates in cylindrical system are, this is r, this is phi and this is z. Now similarly, if we want to find out the spherical coordinate system, so now for the same points, now he is asking us to determine the spherical coordinate system. Now in the spherical coordinate system, we know that we will represent r as capital R and theta, and the other one is phi. And we have already seen that r is equal to square root of x square plus y square plus z square, and theta is equal to cos inverse of z by capital R, and phi is similar to that of cylindrical coordinate system, it is tan inverse of y by x. So now we know the x, y and z values. So first of all, we will compute r. See, r has been computed and it is root 50. I'll write it as pi root 2. And cos theta is z by r. Z I do have 5 and r I have already obtained here, phi root 2. So 5 by pi root 2, it is 1 by root 2. So when cos theta is equal to 1 by root 2, you know that theta is nothing but 45 degrees. And tan phi is equal to y by x, that is 4 by 3. Tan inverse of 4 by 3 is 53.13 degrees. So the coordinates are 1 by root 2, 45 and 53.13 degrees. So these are the rectangular coordinates. Now I want to mention here one thing. Now let us suppose if x is equal to 3 and y is equal to 4. So if I want phi is equal to, I am taking it as tan inverse of 4 by 3. So I am getting as 53.13. Now let us suppose x is equal to minus 3, y is equal to minus 4. So in that case also what I will be getting, phi is equal to tan inverse of minus 4 by minus 3. Again minus minus get cancelled. You people will write it as 53.13. No, it is not correct. Because if you carefully see this indicates a cos component, this indicates a sine component. So whenever you are computing phi, my simple suggestion for you is, if both x and y are positive, x positive and y positive, you will take directly as phi. If both x and y, x negative, y is also negative, you take it as phi plus phi. Because the quadrant must be cos negative, sine negative, so it must be in third quadrant. Okay, if let us suppose x is negative, y is positive, then it is nothing but cos theta is negative, y is positive. So which quadrant? Second quadrant. So you take it as pi minus theta. If x is positive and y is negative, you take it as minus theta. So this you should remember while you are computing phi. Okay. So as of now, since both are positive, I will directly take it as phi. So it is 53.13 degrees. Okay. Next. Now we will move on to the next problem, where we are supposed to convert the vector from one coordinate to. So far we have done only on coordinates. Now we are going to transform the vector from one coordinate system to another coordinate system. So the problem given here is, there is a vector in cylindrical coordinate system, because in cylindrical in Cartesian coordinate system we have seen that the components will be like this. So, or they will be like this, I bar plus j bar k bar, right? Whereas in cylindrical coordinate systems they will be like this, u r, u phi and uz. Whereas in spherical systems there will be capital R, which I am using. So now what he has given a vector which is there in cylindrical coordinate systems, and he wants to transform, determine f in each case in Cartesian form at a point. So at this point he wants to transform this vector into Cartesian form. So first of all, whenever you are transforming a vector, so first thing is you should transform the coordinates, and next is you should transform the vector. See, conversion of coordinates of points, and next is you should transform the components of vector. So first of all, let's see the first problem. This is problem number A, this is problem number B. Now I am going to transform the cylindrical coordinates vector into a vector with Cartesian coordinates. Okay. So now, first of all, the first step, I am going with this problem A only. Now the first step is, given the conversion of points. So first of all, what he is asking, transform the vector into Cartesian form, right? So I'll take first of all the point. The point is being given in rectangular coordinates, because x is equal to 1, y is equal to 1, z is equal to 1. It is in a Cartesian system. So first of all, I'll convert it into respective cylindrical coordinate system. First of all, do you know respective cylindrical coordinate system? R, phi and z. We have done it in the previous case. So R, how will you compute? Square root of x square plus y square, which is square root of, this is x, this is y, this is z. So square root of 1 square plus 1 square, it is root 2. Phi is tan inverse of y by x. So it is tan inverse of 1 by 1. So it is tan inverse 1, it is 45 degrees, and z remains 1. So the values are root 2, 45 degrees and 1. So these are the values of R. R is equal to root 2 and phi, and phi is 45 degrees and z is equal to 1. So now the coordinate, the vector now. What is a vector? If you carefully see, the vector is given as 1 by r ur, which means the other components are, what are the other components? Phi and z. The other components are 0. And r value I have already computed, so its actual value is 1 by root 2 ur plus 0 u phi plus 0 uz. So this is your actual vector now. This vector I am now writing it. This is in cylindrical coordinates. Okay. Now I am going to transform the cylindrical coordinates vector into a vector in Cartesian coordinates. Okay. Now, we have seen already in the last class that the vector, if it is to be transformed from Cartesian to cylindrical, this is the format. These are the coordinates of the vector. These are the vector components in Cartesian form. These are the vector components in cylindrical form. In the cylindrical form, if you see what are the coordinates, the components of vector, in r direction it is 1 by root 2, in phi direction it is 0, in z direction it is 0. So the same I am applying here. See, here it is 1 by root 2, this is 0, this is 0. See, phi value I have already obtained. What is phi value? It is 45 degrees, right? I will substitute these values and I will substitute these values, then automatically I will get these components. Okay, now let's see. See, I have done this one. Cos 45 minus sin 45, sin 45, cos 45. All values I have substituted. And now if you carefully see what I have got, 0.5, 0.5 and 0. So this is AX component, this is Y component, this is Z component. So I will write it simplified. I will remove this one and I will take out 0.5 common. So 0.5 means 1 by 2, so it is 1 by 2 into Ux plus Uy. This is my final vector in Cartesian system. Okay. Now we will move on to the next one in cylindrical system. Now we will move on to sorry, this is actually spherical system. I think in the last, okay. Yeah, this is also in spherical. So actually this, because it is in capital R, right? So this is a spherical one. So I am going to change this one as spherical. So now this vector, this is case number B. This is in spherical format. Now you are supposed to convert it into Cartesian format. Now how to convert this one? Now see, given again, first of all we have to convert it into Cartesian system. So 1, 1, 1 has been given for you. So first of all you have to convert this point into spherical. So r is equal to square root of x square plus y square plus z square. So it is root 3. And theta, you know that it is cos inverse of r by, sorry, z by r. Z is already 1 by root 3. For this one, you are supposed to apply cos inverse. So it is somewhere around 54 degrees. So 54.73. Okay. 54.73 degrees. And phi, it is tan inverse of y by x. Y is 1, z is 1, both are positive. So I can directly take phi. So it is 45 degrees. So now these are the components, root 3, 54.73 and 45. These are the cylindrical coordinates of the points. Now, transforming the vector. So our vector is now this one, right? Sorry, this is spherical. This is our vector. So how to write this vector actually? This is only r component, the other components are 0 basically. And this r value also I have obtained. What is r value? R, theta and phi we have done in the last slide, right? It was root 3 and it was something 57 degrees, it was 45 degrees, right? So I will write it as root 3. Okay, see. That's why I have, see, all these values I know, theta value I know, phi value I know, and this AR also I know, 1 by root 3, A theta is 0, A phi is 0. So I will substitute these values. Now if you carefully see, after transforming, I will get 1 by 3, 1 by 3 and 1 by 3. So which means that this is x component, y component and z component. So I will take a common. See, this is my final vector. This is the way how you will be solving these problems. I hope now you are able to transform the vector from one coordinates to other coordinates. And these are the lecture level problems which you are supposed to perform. Practice them at home.